this video, we'll go over some practice problems involving electromagnetic radiation. Again, a couple of key points I want to hit home. Electrons are neither wave nor particle. They are a combination of both. Electromagnetic radiation contains a vast array of different energy sources, from X-rays, gamma rays, all the way to AM and FM radio waves, which all have their own amplitude and frequency. And another main point is that electromagnetic radiation travels at the speed of light, 3 × 10⁸ meters per second. So having said that, let's go over some practice problems here. Here in this example set, we'll do 2 of them. The wavelength of green light from a traffic signal is centered at 522 nanometers, so that's our wavelength. What is the frequency of this radiation? So green light is part of the visible region of the electromagnetic spectrum. We know that wavelength times frequency is equal to speed of light. So let's solve for frequency. So let's go ahead and write our main equation here. Our main equation is lambda, which is wavelength, times frequency is equal to the speed of light. We have our wavelength here. Let me highlight that in yellow. Let's go ahead and convert that to meters, just to get the units to cancel out. So I'm going to go ahead and do that. So the conversion is 1 nanometer contains 1 × 10⁻⁹ meters. Nano is the prefix denoting -9. So doing that on my calculator, again, just to show you that the nanometers cancel. And leaving us with meters, we get 5.22 × 10⁻⁷ meters. That will be your wavelength. We already know C is a constant. I'll give you that on any examinations. So all we need to do now is solve for frequency V. Now remember, the units of V are in hertz. Hertz basically means 1/seconds or inverse seconds. So solving for V here and recognizing our constant C, dividing it by the wavelength we've calculated here in meters, I'll highlight that in green. I'm getting an answer of 5.75 × 10⁻⁴ hertz. So that green light, that wave is traveling to your eyes at this speed, 5.75 × 10⁻⁴ inverse seconds, 1/seconds. In practice problem number 2, we'll utilize the fact that these electromagnetic radiations actually have an energy imparted to them. So that energy can be calculated using this formula here. The energy is equal to Planck's constant times frequency measured in hertz. So these are waves, but if you notice clearly in this problem here, I'm going to highlight the word photon in green. We're talking about energy in the form of particles. Photon is a special term designating a particle of light. We could just as well talk about it in terms of wavelength and frequency, but we can also talk about it in terms of photons. So we can have it both ways. That's wave-particle duality. So a photon of wavelength 5 × 10⁴ nanometers, that turns out to be in the IR infrared region of the electromagnetic spectrum. Use infrared a lot in remote controls, stuff like that. So how much energy is actually inputted in this wavelength? So let's go ahead and solve that utilizing this equation. Well, we're not given the frequency, we're given the wavelength, but we can't calculate the frequency, realizing that electromagnetic radiation once again travels at the speed of light, 3 × 10⁸ meters per second. So this is the answer for part A that we're going to do together. First thing is I'm going to convert this nanometers to meters. That's always a good thing to do. Get it to the SI base unit. The SI base unit of length is meters. So 1 nanometer is 1 × 10⁻⁹ meters. And now let's calculate for the frequency, realizing that wavelength times frequency is equal to C, which is speed of light. So I've kind of skipped a little bit of the algebra here. I went ahead and solved for frequency V, which is nothing more than speed of light divided by wavelength. And doing that, the meters cancel out with the meters, and the seconds that's in the denominator on top of the numerator actually gets shifted down to the denominator, and you're left with inverse seconds. Inverse seconds is nothing more than hertz. And so that is the frequency that corresponds to this wavelength. And now the energy that's involved in this packet of energy is equal hv. E is equal to hv. Well, Planck's constant is a constant. Energy has the customary units of joules. So let's go ahead and solve for this. So utilizing this equation, Planck's constant is something that I'll give you. Definitely do not memorize it. Times, so Planck's constant times the frequency, which we solved above here. I'm going to highlight this in green. And the seconds cancels out with the inverse seconds. Remember, this is seconds inverse, or seconds to the -1 makes that seconds go to the denominator. So seconds cancel, we're left with joules. The energy of an infrared photon or radiation in the infrared region of the electromagnetic spectrum is pretty small, 3.98 times 10 to the -21 joules. I'll highlight the answer in yellow. How about part B? Part B is a photon that has a much smaller wavelength, and it's 5 times 10 to the -2 nanometers. Very, very small wavelength. We would expect a very large frequency. And this thing is really, really a fast-moving wave, X-rays, a lot of energy in those high-frequency waves. So let's go ahead and use the same pipeline to solve for this. So go ahead and converting part B to meters, our wavelength is 0.05, 5 times 10 to the -2 nanometers. And, I always like to cancel out my units, leaving me with meters. And let's go ahead and solve for the fact that the velocity is equal to the speed of light over wavelength. So speed of light is given to us here as c. The wavelength that we calculated is 5 times 10 to the -11 meters. Let's just go ahead and highlight this in a purple color, even though it doesn't look that pretty. Solving for this, the meters cancel. We're left with this frequency. So this frequency corresponds to this wavelength. The energy that's impacted by that or contained in that photon, that X-ray that has this wavelength and this frequency is E equals hv, Planck's constant times our frequency. And we're getting an answer here of 3.98 times 10 to the -15 joules. For this, I'll highlight it in green. So notice here we have a small energy, 10 to the -21. And here we have a smaller wavelength, but a little bit larger energy, even though 10 to the -15 is pretty small compared to 10 to the -21. 10 to the -15 is a huge number. So the key point here is that there's energy in these packets, this quanta, and the energy is small, but it is enough. I mean, this is the energy that, remember this problem in part A was the green light from the traffic signal. That's energy that's being absorbed by your eye. And here, this is energy in the form, remember part B is an X-ray photon. And that's some pretty powerful energy.